Good morning and welcome to QCon. So as Nikki mentioned, we're going to start with something that has a 90% chance of failure. So I want to request all of you to take out your phones or laptops and go to this URL on the screen, tiny.cc/QConLive. You can also scan this QR code and log in with your LinkedIn credentials. If you don't have a LinkedIn account, please make one right now. You should see a live stream of this very talk delayed by a minute. And my lovely wife sitting here in the audience is streaming the demo live from her phone. So if you're successful, you should see something like this on your screen. How many of you are able to see something? Awesome. All right, I guess you're getting there. You're still making a LinkedIn account, right? All right, so this comments area is where you can interact with each other. You can post comments, you can ask questions, and I will try and answer some of them at the end of this talk. The only thing I request is to not share the stream because this is just a demo, and I will delete it after the end of this talk. All right, let's start with a question. Anyone know what the largest live stream in the world was? Think of something that grinds an entire nation to a halt. Yes? Nope.
Royal wedding.
Oh, that was the second largest. Yes.
Cricket match.
Yes, cricket. All right, so believe it or not, it was the semi-final of the Cricket World Cup last year between India and New Zealand. More than 25 million viewers watched the match at the same time. Also, overall, the match crossed 100 million viewers. And as this gentleman said, the second largest was the British royal wedding, which was more than 18 million viewers concurrently. So remember this, we'll come back to this. So this is me and my team. We call ourselves the Unreal Real-Time Team, and we love cricket, and we love coding. This has a range. Not very great. And we believe in something. We believe that problems in distributed systems can be solved by starting small. Solve the first problem and add simple layers in your architecture to solve bigger problems. And today, I'm going to tell you a story of how we built a platform called the Real-Time Platform, using that principle to solve how we can stream or have many, many people interact simultaneously on live videos. I hope that a lot of you will be able to learn something from this and also apply it to your own systems. So what is a live video? A live telecast, a live conference broadcast, a sports match, all of them are examples of live videos. How many of you have interacted with a live stream on YouTube or Facebook? Perfect. So you know the general idea. The difference that these streams have is that they allow users or viewers to interact with each other. So what is a real-time interaction on live video? So the easiest way is to just look at it or try it on your phones with the demo. People are able to like, comment, and just ask questions and interact with each other. So this is an example of a LinkedIn iOS app doing a LinkedIn live video. And similarly, on desktop, the experience is very similar. There are many rich interactions that happen there. This particular live stream is from the LinkedIn Talent Connect conference that happened in September of last year. So I want to talk about the simplest interaction here, which is how do these likes get distributed to all these viewers in real time, all at the same time? So let's say that a sender S likes the video and wants to send it to a receiver A. So the sender S sends the like to the server with a simple HTTP request. But how do we send the like from the server back to the receiver A? Publishing data to clients is not that straightforward. So this brings us to the first challenge. What is the delivery pipe to send stuff to the clients? By the way, this is how I've structured the presentation today. I'm going to introduce problems, and I'm going to talk about how we solve them in our platform. And these are all like simple layers of architecture that we added to our platform to solve each of them. So as discussed before, the sender S sends the like to what we call the likes backend, which is the backend that stores all these likes, with a simple HTTP request. And this backend system now needs to publish the like over to the real-time delivery system. Again, that happens with a simple HTTP request. So the thing we need is a persistent connection between the real-time delivery system and the receiver A. So let's talk a little bit more about the nature of this connection, because that's the one that we care about here. So once again, log in at linkedin.com. Hopefully you've created an account by now. And go to this URL, tiny.cc/realtime. This time, you will actually see what's happening behind the scenes. You should be logged in for this. Right, so for those of you who were successful, you should see something like this on your screen. This is literally your persistent connection with LinkedIn. This is the pipe that we have to send data over to your phones or to your laptops. And this thing is extremely simple. It's a simple HTTP long pole, which is a regular HTTP connection where the server holds on to the request. It just doesn't disconnect it. So over this connection, we use a technology called server-sent events. And this allows us to stream chunks of data over what is called the EventSource interface. And the client doesn't need to make subsequent requests. We can just keep streaming data on the same open connection. So the client makes a normal HTTP GET request. It's as simple as a regular HTTP connection request. The only difference is that the accept header says event stream. That's the only difference from a regular HTTP connection request. So the server responds with a normal HTTP 200 OK and sets the content type to event stream. And the connection is not disconnected. Chunks of data are sent down without closing the connection. So you might receive, for example, a like object, and later you might receive a comment object. Without closing the connection, the server is just streaming chunks of data over the same open HTTP connection request. Each chunk is processed independently on the client through what is called the EventSource interface. And as you can see, there is nothing terribly different from a regular HTTP connection, except that the content type is different, and you can stream multiple chunks of bodies on the same open HTTP connection request. How does this look like on the client side on web? The client first creates an EventSource object with the target URL on the server. And then it defines these event handlers, which will process each chunk of data independently on the client. So most browsers support the EventSource interface natively. On Android and iOS, there are lightweight libraries that are available to implement the EventSource interface on these clients. OK, so we now know how to stream data from the server to the client, and we did this by using HTTP long pole with server-sent events. What is the next challenge? Yes, so think of all the thousands of Indians trying to watch cricket, right? The next challenge is multiple connections, maybe thousands of them. And we need to figure out how to manage these connections, right? So connection management. At LinkedIn, we manage these connections using akka. Akka is a toolkit for building highly concurrent, message-driven applications. Anyone familiar with akka actors? Wow, room full. So yes, not Hollywood actors. They're this very simple thing. It's this little small guy. So this is the only concept you need to know to understand the rest of the presentation. Akka actors are objects which have some state, and they have some behavior. The behavior defines how the state should be modified when they receive certain messages. Each actor has a mailbox, and they communicate exclusively by exchanging messages. An actor is assigned a lightweight thread every time there is a message to be processed. And that thread will look at the behavior that is defined for that message and modify the state of the akka actor based on that definition. And then once that is done, this thread is actually free to be assigned to the next actor. Since actors are so lightweight, there can be millions of them in the system, and each can have their own state and their own behavior. And a relatively small number of threads, which is proportional to the number of cores, can be serving these millions of actors all at the same time. Because a thread is assigned to an actor only when there is something to process. So in our case, each actor is managing one persistent connection. That's the state that it is managing. And as it receives an event, the behavior here is defining how to publish that event to the event source connection. And thus many connections can be managed by the same machine using these concept of ACA actors. So let's look at how an ACA actor is assigned to an event source connection. Almost every major server framework supports the event source interface natively. At LinkedIn, we use the Play framework. And if you're familiar with Play, we just use a regular Play controller to accept the incoming connection. And then we use the Play event source API to convert it into a persistent connection and assign it a random connection ID. Now we need something to manage the life cycle of these connections, and this is where ACA actors fit in. And so this is where we create an ACA actor to manage this connection. And we instantiate an ACA actor with the connection ID and the handle to the event source connection that it is supposed to manage. So let's get back out of code and see how the concept of ACA actors allows you to manage multiple connections at the same time. So each client connection here is managed by its own ACA actor. And each ACA actor, in turn, all of them are managed by an ACA supervisor actor. So let's see how a like can be distributed to all these clients using this concept. So the likes backend publishes the like object to the supervisor ACA actor over a regular HTTP request. The supervisor ACA actor simply broadcasts the like object to all of its child ACA actors here. And then these ACA actors have a very simple thing to do. They just need to take the handle of the event source connection that they have and send the event down through that connection. So for that, it looks something very similar. Very simple. It's event source.send and the like object that they need to send. So they will use that to send the like objects down to the clients. And what does this look like on the client side? The client sees a new chunk of data, as you saw before, and will simply use that to render the like on the screen. So as simple as that. Okay, so in this section, we saw how an event source connection can be managed using ACA actors, and therefore you can manage many, many connections on a single machine. What's the next challenge? Sorry? Fan out is one. Build before that?
Queue size, mailbox.
Oh, mailbox queue size. Oh, we're now talking already about big scale. Even before that, something simple. I'll give you a hint. My wife and I always want to watch different shows on Netflix. No? Yes, so the thing that we did just now is just broadcast the like blindly to everybody, right? Without knowing which particular live video they're currently actually watching, right? So the next challenge is different clients watching different live videos. How do we handle that? We don't know how to make sure that a like for, let's say, the red live video goes to the red client and the green live video goes to the green client. All right, so let's assume that this client here with connection ID 3 is watching the red live video, and this client here with connection ID 5 is watching the green live video. So what we need is a concept of subscription. Right? So the client can inform the server that this is the particular live video that they're currently watching. So when client 3 starts watching the red live video, all it does is that it sends a simple subscription request using a simple HTTP request to our server. And the server will store the subscription in an in-memory subscriptions table. So now the server knows that the client with connection ID 3 is watching the red live video. Question, why does in-memory work? Right? So there are two reasons. The subscription table is completely local. It is only for the clients that are connected to this machine. And secondly, the connections are strongly tied to the life cycle of this machine. If the machine dies, the connection is also lost. And therefore, you can actually store these subscriptions in memory inside these front-end nodes. And we'll talk a little bit more about this later. So similarly, client 5 also subscribes to live video 2, which is the green live video. So once all the subscriptions are done, this is the state of the front end or the real-time delivery system. The server knows which clients are watching which live videos. So when the backend publishes a like for the green live video this time, all that the supervisor actor has to do is figure out which are all the clients that are subscribed to the green live video, which in this case is clients 1, 2, and 5. And so the corresponding actors are able to send the likes to just those client devices. Similarly, when a like happens on the red live video, the supervisor actor is able to decide that it is destined only for connection IDs 3 and 4, and is able to send them the likes for the videos that they're currently watching. All right, so in this section, we introduced the concept of subscription, and now we know how to make sure that clients are only receiving likes for the videos that they're currently watching. So what's the next challenge? Now we can go back to the gentleman here. So somebody already said here that there could be millions and millions of connections, right? Like now, there's just more number of connections than what a single machine can handle, right? That's the next challenge. So we thought really hard about this, right? Like this is where we were a little stuck. And that's us thinking really hard. And we finally did what every backend engineer does to solve scaling challenges, right? You already know. We added a machine, right? So we add a machine and we start calling these front-end servers. The animation worked. And we introduce a real-time dispatcher, right? Whose job is to dispatch a published event between the newly introduced front-end machines, because now we have more than one. Now, can the dispatcher node simply send a published event to all the front-end nodes? Yes, it can. It's not that hard. It can, but turns out that it's not very efficient if you have a small live video with only a few viewers that are connected to just a few front-end machines, right? And there's a second reason which I'll come back to a little later. But for now, let's assume that the dispatcher can't simply send a like to all the front-end machines blindly. So given that, the dispatcher now needs to know which front-end machine has connections that are subscribed to a particular live video. And so we need these front-end machines to tell the dispatcher whether it has connections that are subscribed to a particular live video. So let's assume that front-end node 1 here has connections that are subscribed to the red live video. And front-end node 2 here has connections that are subscribed to both the red and the green live video. So front-end node 1 would then send a simple subscription request, just like the clients were sending to the front-end servers, and tell the real-time dispatcher that it has connections that are watching the red live video. And the dispatcher will create an entry in its own subscriptions table to figure out which front-end nodes are subscribed to which live videos. Similarly, node 2 here subscribes to both the red live video and the green live video. Now let's look at what happens when an event is published. So after a few subscriptions, let's assume that this is the state of the subscriptions in the real-time dispatcher. And note that a single front-end node could be subscribed to more than one live videos, right? Because now it can have connections that are watching multiple live videos at the same time. So in this case, for example, node 2 is subscribed to both the red live video and the green live video. So this time, the likes backend publishes a like on the green live video to the real-time dispatcher. And the dispatcher is able to look up its local subscriptions table to know that nodes 2, 3, and 5 have connections that are subscribed to the green live video. And it will dispatch them to those front-end nodes over a regular HTTP request. And what happens next? That you've already seen. These front-end nodes will look up their own in-memory subscriptions table that is inside them to figure out which of their connections are watching the green live video and dispatch the likes to just those clients. Make sense? All right, so we now have this beautiful system where the system is able to dispatch between multiple front-end nodes, which are then able to dispatch to many, many clients that are connected to them. And we can scale to almost any number of connections. But what is the bottleneck in the system? The dispatcher is the bottleneck in the system. It never ends. So the next challenge is that we have this one node, which we're calling the dispatcher, and if it gets a very high published rate of events, then it may not be able to cope up, right? So that takes us to challenge number 5, which is a very high rate of likes being published per second. So once again, how do we solve scaling challenges? We add a machine, right? And I mean, engineers just do the most lazy thing, and it usually works out pretty well. So we add another dispatcher node to handle the high rate of likes being published. And something important to note here. The dispatcher nodes are completely independent of the front-end nodes. Any front-end node can subscribe to any dispatcher node, and any dispatcher node can publish to any front-end node. There is no persistent connections here, right? The persistent connections are all only between front-end nodes and the clients, not here. And this results in another challenge. The subscriptions table can no longer be local to just one dispatcher node, right? Any dispatcher node should be able to access that subscriptions table to figure out which front-end node a particular published event is destined for. And secondly, I tricked you a little bit before. This subscriptions table can't really live in memory in the dispatcher node. I mean, it can live in the memory in the front-end node, but not in the dispatcher node. Why? Because even if a dispatcher node is lost, let's say this one just dies, then we can't afford to lose this entire subscriptions data, right? And so for both of these reasons, we pull out this subscriptions table into its own key value store, right? Which is accessible by any dispatcher node at any time. So now, when a like is published by the likes backend for the red live video on a random dispatcher node, and on the green live video to some other random dispatcher node, each of them are able to independently query the subscriptions table that is residing in the key value store. And they're able to do that because the subscriptions table is completely independent of these dispatcher nodes, and the data is safe there. So now the dispatcher nodes dispatch the likes based on what is in the subscriptions table over regular HTTP requests to the front-end nodes. Cool? All right, so I think we now have all the components to show you how we can do what I promised in the title of this talk. Anyone remember the title of this talk? Oh, thank God, I'm not that boring, huh? All right. So if 100 likes are published per second by the likes backend to the dispatcher, and there are 10K viewers that are watching the live video at the same time, then we're effectively distributing 1 million likes per second. So I'm going to start from the beginning and show you everything in one flow, because everyone tells me that I got to repeat myself if I got to make sure that you will remember something when you walk out of this talk. So this is how a viewer starts to watch a live video. And at this time, the viewer is, the first thing that the viewer needs to do is subscribe to the front-end node and subscribe to the live video topic that they're currently watching. So the client sends a subscription request to the front-end node. And the front-end node stores the subscription in the in-memory subscriptions table. And the same happens for all such subscriptions from all the clients. So let's go back to our overall diagram. Perfect. So now the subscription has reached the front-end nodes. So the front-end node, as I said before, now has to subscribe to the dispatcher nodes, because the dispatcher will need to know during the publish step which front-end nodes have connections that are subscribed to a particular live video. So let's look at that flow. The front-end node sends a subscription request to the dispatcher, which creates an entry in the key value store that is accessible by any dispatcher node. So in this case, node 1 has subscribed to live video 1, and node 2 is subscribing to live video 2. So this is the end of the subscriptions flow. So now we need to look at what happens during the publish flow. So the publish flow starts when a viewer starts to actually like a live video. And so different viewers are watching different live videos, and they are continuously liking them. And all these requests are sent over regular HTTP requests to the likes backend, which stores them and then dispatches them to the dispatcher. So it does so with a regular HTTP request to any random dispatcher node, and they look up the subscriptions table to figure out which front-end nodes are subscribed to those likes, and dispatch them to the subscribed front-end nodes. Okay, so the likes have now reached the front-end nodes, and we have the last step, which we began the presentation with. They need to send it to the right client devices. So each front-end node will look up its local subscriptions table, and this is done by the supervisor ACA actor to figure out which ACA actors to send these like objects to. And they will dispatch the likes to the appropriate connections based on what they see in the subscriptions table. And done. We just distributed 1 million likes per second with a fairly straightforward and iteratively designed scalable distributed system. So this is the system that we call the real-time platform at LinkedIn. By the way, it doesn't just distribute likes. It can also do comments, typing indicators, scene receipts. All of our instant messaging works on this platform. And even presence, those green online indicators that you see on LinkedIn, are all driven by this system in real time. So everything is great. We're really happy. And then LinkedIn adds another data center. Now, this made us really stressed. We don't know what to do. So we went back to our principal. We said, OK, how can we use our principal to make sure that we can use our existing architecture and make it work with multiple data centers? So let's look at that. So let's take the scenario where a like is published to a red live video in the first data center. So this is DC1. Let's just assume that this is the first data center. And let's also assume that there are no viewers of the red live video in the first data center. So this is where, remember I spoke about subscriptions in the dispatcher? It helps here, because now we might prevent a lot of work in DC1 because we know whether we have any subscriptions for the red live video in DC1. We also know that there are, well, in this case, there are no viewers for the red live video in DC2. But there are viewers of the red live video in DC3, right? So somehow we need to take this like and send it to this guy over here, right? Really far away. So let's start. The likes backend gets the like for the red live video from the viewer in DC1, and it does exactly what it was doing before, right? Because it's not the likes backend's responsibility. It's the platform's responsibility, right? We are building a platform here, and therefore hiding all the complexity of the multiple data centers from the users that are trying to use this platform, right? So it will just publish the like to the dispatcher in the first data center, just like it was doing before. Nothing changes there. And now that the dispatcher in the first data center has received the like, the dispatcher will check for any subscriptions, again, just like before, in its local data center. And this time, it saved a ton of work because there are no viewers of the red live video in DC1. But how do we get the like across to all the viewers in the other data centers, right? Like, that's the challenge. Any guesses? I'm sorry?
Add another dispatcher.
No, don't add another dispatcher. We already have too many dispatchers.
This dispatcher behaves like the front-end for the other dispatcher.
OK.
So the DC3's dispatcher can connect and register as if it's a front-end.
Okay, so we can do cross-colo subscriptions, cross-data center subscriptions. What's another idea? Good, broadcast to any DC. And we'll talk a little bit about like the trade-off between subscribing in a cross-data center fashion versus publishing in a cross-data center fashion. So it turns out that publishing in a cross-data center fashion is better here, and we'll talk a little bit about that a little later. So yes, this is where we do a cross-colo or a cross-data center publish to dispatchers in all of the peer nodes, right? And we're doing that so that we can capture viewers that are subscribed to the red live video in all the other data centers. So the dispatcher in the first data center simply dispatches the likes to all of its peer dispatchers in all the other data centers. And in this case, a subscriber is found in DC3, but not in DC2. Right? That's the only, and by the way, this dispatcher is doing exactly what it would have done if it received this like locally in this data center. There's nothing special that it is doing. Right? It's just that this dispatcher distributed the like all over to all the dispatchers in the peer data centers. And the viewer in DC3 simply gets the like just like it would normally do because the dispatcher was able to find the subscription information in DC3. And this viewer with the green live video does not get anything. All right, so this is how the platform can support multiple data centers across the globe by keeping subscriptions local to the data center while doing a cross-colo fan-out during publish. Make sense? All right, so finally, I want to talk a little bit about the performance of the system. Because like everybody here is here because, hey, scale, right? All right, so we did this experiment where we kept adding more and more connections to the same front-end machine. Like we just kept on going. And we wanted to figure out how many persistent connections a single machine can hold. So any guesses? Oh, 1 million, wow. No, not that many. We also are doing a lot of work. Sorry? Yeah, so he's very close. So it turns out that we were able to have 100,000 connections on the same machine. Yes, you can go to 1 million, but at the same time, because we're also doing all this work, and because we use the system not just for distributing likes, but also for all the other things that LinkedIn has, we were able to get to 100,000 connections per front-end machine. All right, so anyone remember the second largest live stream?
Royal wedding.
Royal wedding. All right, so the royal wedding had 18 million viewers at peak. And so we could do that. So we could do that with just 180 machines, right? Because a single machine can do 100,000 connections. And so with 180 machines, you're able to have persistent connections for all the 18 million viewers that are currently streaming the royal wedding. Of course, we just didn't get to this number easily. So we hit a bunch of file descriptor limits, port exhaustion, even memory limits. And luckily, we documented all of that at this link, tiny.cc/LinkedIn scaling. And I hope that you will be able to get something out of reading something like this. Because it's very interesting. It's just like regular scaling challenges. It's just that we hit it in context of trying to expand the number of connections that we could hold on a single machine. All right, how about other parts of the system? How many events per second can be published to the dispatcher node? Again, before you answer this question, I want to talk about something really important about the design of the system, which makes it massively scalable. The dispatcher node only has to publish an incoming event to a maximum of the number of front-end machines, right? It doesn't have to worry about all the connections that these front-end machines are in turn holding. It only cares about this green fan-out here, which is the number of front-end machines that this dispatcher can possibly publish an event to. But it doesn't have to worry about this red fan-out, because that's the part that the front-end machines are handling. And they're doing that with in-memory subscriptions, with ACA actors, which are highly, highly efficient at this. Right? Okay. So now with that context, what do you think is the maximum events that you can publish to this dispatcher per second?
10,000 square.
Very close. That's a very, very good guess. So it turns out, for us, that number turned out to be close to 5,000. So 5,000 events can be published per second to the dispatcher node, to a single dispatcher node. And effectively, we can publish a 50,000 likes per second to these front-end machines with just 10 dispatcher machines. By the way, this is just the first part of the fan-out, right? These 50,000 likes per second will then be fanned out even more by all the front-end machines that are able to do that very, very efficiently. So that's a multiplicative factor there, and that will result in millions of likes being distributed per second. So lastly, let's look at the time, because everybody really, really cares about latency, right? Like you're building a real-time system, so you got to make sure that things are super fast, right? So let's talk about the end-to-end latency. All right, so if we record the time t1 at which the likes backend publishes the like to our real-time platform, which is the dispatcher machine, and we record the time t2 at which point we have sent the like over the persistent connection to the clients. And the reason we are measuring it there is because you can't really control the latency outside your data center, right? I mean, you have some control over it, but that's the one that the platform really, really cares about. Then the delta turns out to be just 75 milliseconds at P90. The system is very fast, as there is just one key value lookup here, right? And one in-memory lookup here, and the rest is just network hops. And very few network hops. So these are some performance characteristics of the system. Now this end-to-end latency measurement is also a very interesting thing. How do you really do that, right? Because most of you must be familiar with measuring latencies for a request response system. Like you send an incoming request, and the same machine can measure when the response is sent out, and therefore you can say that, hey, it took this much time. In this case, there are multiple systems involved. You're going from the dispatcher to the front-end node, and then to the client. How do you measure latencies for such one-way flows across many, many systems? So that is also a very interesting problem, and we wrote about it. We wrote about a system that we built using nearline processing, using SAMSA. So SAMSA is another technology that we use at LinkedIn. And you can use that to understand how latencies, you can measure latencies across end-to-end systems across many, many machines. So we wrote about it at tiny.cc/LinkedIn latency. Don't have the time to dive into it here, although I would love to. And you should, I hope that you get something out of reading something like this. And if you have a system where you want to measure latencies across many different parts of the stack, you can use something like this to measure latencies. So why does the system scale? I think it scales because it is, you can add more front-end machines or more dispatcher machines as your traffic increases. It's just completely horizontally scalable. The other thing that I mentioned at the beginning of this talk is that we also extended the system to build presence, which is this technology where you can understand when somebody goes online and offline. And now that we have these persistent connections, we know when they were made, we know when they were disconnected. So we also know when somebody came online and when somebody went offline. But it isn't that easy, because mobile devices are notorious, right? Like they will sometimes just have a bad network, they might disconnect and reconnect without any reason. So how do we kind of average out or reduce all that noise to kind of figure out when somebody's actually online and when they're offline, and not just jitter all the way where you keep going offline and online because you have connections and disconnections simply because of the network that you have. So we wrote about that at tiny.cc/LinkedIn presence, where we use the concept of persistent connections to understand how somebody goes online and offline, and we built the presence technology on top of the exact same platform. So I hope that is also useful to you. All right, so that was probably a lot to consume in the last few minutes. So I'll try to see if I can help you remember some of this. Real-time content delivery can enable dynamic interactions between users of your apps. You can do likes, you can do comments, you can do polls, discussions, very powerful stuff because it really engages your users. And the first piece you need is a persistent connection. For that, there is built-in support for EventSource in most browsers and also on most server frameworks. So there are also easily available client libraries that you can use for iOS and Android. Play and actors are powerful frameworks to manage connections in a very efficient way. They can allow millions of connections to be managed on your server side. And therefore, they can allow millions of viewers to interact with each other. So everyone remember ACA actors? Way cooler than Hollywood actors. The principle I started this presentation with, that challenges in distributed systems can be solved by starting small, solve the first problem, and then build on top of it. Add simple layers in your architecture to solve bigger challenges. This is all we did throughout this presentation. And when you hit a limit, horizontally scaling the system is usually a good idea. Add a machine, distribute your work. And the real-time platform that I described to you can be built on almost any server or storage technology. You can use Node.js, you can use Python. All of these server frameworks support some methodology of maintaining persistent connections. And for the key value store, you can use Couchbase, Redis, MongoDB, anything that makes you the happiest, right? Anything that you are already using. And so most importantly, you can do the same for your app. Real-time interactions are very powerful. And I feel that if you use some of the principles that I shared with you, you can do some pretty interesting stuff and pretty dynamic experiences in your own apps. Thank you, everyone, for attending this session. I'm a proud Indian. I work at LinkedIn in the US, and I'm so glad that I got this opportunity to talk to you here at KubeCon London. This talk and all of its slides will be available at tiny.cc/KubeCon2020, I'm assuming very soon. And there is also an AMA session at 1:40 p.m. where you can come and ask me anything, not just related to this, but anything else that you have in your mind. And that's happening at Guild. One more thing. So now that we have about 9 minutes left, I wanted to check on the stream. I don't know if it's still playing. It is. Nobody said anything? Wow. All right, questions?
Like we're going to have an orderly queue. If you can just come here, then I think that's how it works in this one.
Hello, thanks for that. Very interesting. Do you have any fallbacks for clients that don't support server-sent events, or do you just say modern browsers are our focus here?
Great question. So the question was, do we have any fallbacks if server-sent events don't work? So the beauty of server-sent events is that they are literally a regular HTTP request. There's absolutely no difference between what a regular HTTP connection would do. In fact, WebSockets is something that sometimes gets blocked by firewalls in certain systems. And we have never experienced a case where server-sent events don't work because it's a regular HTTP connection. Most firewalls will not block it, and most clients would understand it, and we've never seen a case where server-sent events doesn't work. Yes.
Hello. So how do you synchronize your video stream with your likes, with time, basically?
Oh, I see. So I think the question here is that once these likes have happened, how do you make sure that the next time somebody watches this video, the likes show up at the same time? Is that what you're asking?
Yeah, and also I guess the video streams are delayed a little bit on different servers, and your likes are happening in different places.
I see.
How do you do that?
I see. So yes, I think you must have noticed here that there is a delay, right? And I think the question here is that, hey, I liked at moment X, but maybe the broadcaster sees it at moment Y, right? So yes, there is a delay, and some of it is simply because of natural causes, like you just speed of light. And the other is that there's also sometimes something that we do to make sure that the broadcaster can like cut something off if something is seriously wrong. The good thing here is that once somebody has pressed like, it will show up to all the viewers almost instantaneously. Like you can actually try it right now. If you press like, you should actually be able to see it almost immediately. So the distribution is real time. But yes, there may be a delay between when you think that the broadcaster said something versus when you actually liked it. And that is natural. I think there are also security reasons to do so.
Yeah, hi. First of all, thanks for your talk.
Thank you.
My question is, do you have any consistency guarantees, especially in view of dispatcher failure, even across data centers?
Yes, great question. What about consistency, right? Like how do you show guarantees? How do you make sure that a like will actually get to its destination? Short answer is that we don't, right? Because in this case, what we are going for is speed, and we're not going for complete guarantees for whether something will make it to the end. Having said that, we measure everything, right? We measure the cross-color dispatch, we measure the dispatchers sending requests to the front ends, and we also measure whether something that was sent by the front end was actually received by the client. And if we see our 4 nines or 5 nines falling, we will figure out what the cause is and we will fix it. Now, I do want to share something else now that you asked this question, which is Kafka, right? I mean, a natural question is like, why not just do this with Kafka? And if we do it with Kafka, then yes, you do get that, because the way you would do it with Kafka is that the likes backend would publish a like over to a live video topic that is defined in Kafka, and then each of these front-end machines would be consumers for all the live video topics that are currently live, right? So you already see a little bit of a problem here, which is that these front-end servers are now responsible for consuming every single live video topic, and each of them needs to consume all of them, because you never know which connection is subscribed to which live video and connected to this front-end server. But what this gives you is guarantees, right? You cannot drop an event anywhere here in the stack, but you can drop an event when you send it to the client from the front-end server. But you can detect that. In fact, EventSource interface provides a built-in support for it. It has this concept of where you are, like it's like a number that tells you where you are in the stream. And then if that things get dropped, the front-end server, the next time it connects, it will tell you that it was at point X, and the front-end server can start consuming from that topic at point X. But what you give away here is speed, and also the fact that the front-end servers would stop scaling after a while, because each of them need to consume from each of these streams. And as scale grows, that doesn't, like as you add front-end machines, that doesn't help, because each front-end machine now needs to still consume all the events from all the Kafka topics.
Yeah, thanks a lot.
Hello. So question related to so you have 100 connections to the clients.
Yes.
Some of the clients are very slow. They might not be consuming your data properly on the pipe.
Okay.
How do you ensure that you don't have memory exhaustion on the servers?
Great question. So notice that when the front-end server sends the data or has the persistent connection to the client, it is actually a fire and forget, right? The front-end server itself is not blocking on sending the data to the client. It just shoves it into the pipe and forgets about it. So there is no process or no thread that is waiting to figure out whether the data actually went to the client. And so therefore, no matter what these clients are doing, they might be dropping events, they might not be accepting it because something is wrong on the client side. The front-end server is not impacted by that. The front-end server's job is to just dispatch it over the connection and be done with it. Again, because we are going for speed and not for guarantees. Yes.
So maybe you can grab them afterwards. But please give Atlas a great name.
Thank you.